Yes. Okay. So today we're gonna have two chunks, part 2 and part 3. So it's going to be a 2 hours thing. I think we're gonna make a short pause in the middle, just to, just to take a breath. And today lecture will be a little bit more. I would not say complicated, but it's a little bit more deep in the sense that there will be probably, even less mathematics than yesterday, but a little bit more of conceptual, sophistication, which needs some time to actually be digested. And so I will take it easy, and you will ask me if things are immediately confused, and I will try to do my best to actually help. So yesterday we were just where at the point where we introduce the important building block of any inference. The inference is the process by which one uses measurements to determine values of theory parameters, and the model is the basis of this, because it's a mathematical structure which I symbolically identified as P of data given the physics, and this vertical bar is important, is a conditional symbol. You set the physics and you get the data. So P of the data given the physics, which in symbols is P of X given M in my convention. And this is a probability model. So this is a mathematical structure that determines the fact that you do not know exactly which data you will get once, even if you knew the true value of the theory parameter M. And of course, I don't need to remember you, but please keep in mind that both data X and parameter M can be multidimensional. I mean, in this notation, they are one-dimensional, but there is actually no bound there. And the model is something that is, you might remember yesterday I mentioned that there are two schools, so-called, of statisticians, the Bayesian and frequentist. I mean, this is already a simplification, and both schools, even if after they diverge on the interpretation of the data, they do not diverge until here. The model is the common piece that both schools need to take and assume for their inference. So the model P of data given physics gives the probability to observe certain data assuming some physics. And this is what some people call the forward process. So the process that brings you from the physics to the data, okay? And this process happens when you run an experiment, because of course, the physics is there, you just don't know it, and all you see is the data. And it also happens when you run simulation, where you know the physics because you have written it into your simulator, even though it's not necessarily the true physics that nature has, and you produce simulated data. However, what is more relevant for learning about nature is the so-called backward process. So the process that once you get the data, brings you back to the physics. And this is actually the inference thing, that's what is called inference. And inference is not possible using the certainty of deductive logic, but it needs a probability statement. So every statement here is associated with some kind of probability or confidence or uncertainty, etc. So the word probability has already occurred various times in this lecture, so maybe it's a good time now to try to define it a little bit better. So, and perhaps the mathematical definition that is most suitable for probability is the one from Kolmogorov, in which is called the set theoretical axiomatic definition. And basically, if you have a statistical experiment, and you define the set omega, big omega, of all the possible mutually exclusive outcome of this experiment. So it can have outcome A, B, C, etc. An event A is a set of one or more elementary outcomes. And then you assume that the probability is an additive function on the set, and it's measurable on a continuous scale so that it can be, it maps on the real axis. It can be represented by a real number. And then you have the axioms here. So the probability of any elementary outcome or of any set of elementary outcome is non-negative. The probability sum over all possible outcomes, so the sample space omega, is equal to 1. And the probability for observing A or B, where A or B are either elementary outcomes or sets of elementary outcome, is P of A plus P of B, assuming that A and B are disjoint sets. Okay? So this is the mathematical side, and it's of course, it's rigorously true, but it's also an abstract concept that cannot be measured and probably needs an operational definition to be applied because it's too broad to map into one single operational definition of probability. So this is where it becomes interesting for us. What are the operational definition of probabilities? There are, historically, there have been 3 times. The first one is probably, so one of the first was from Laplace, the combinatorial definition. If an elementary event A can occur in a number n of distinct and equally likely ways, and if identified as little n the number of favorable cases, favorable defined by the, the operator in this case, then the probability is the ratio between the number of favorable cases and the total possible outcomes, n over n, small n over big N. This has been, it's a more general definition, which is the frequency theory definition, in which basically is the same thing, except that we're taking the limit for the number of trials going to infinite. So this is still the probability in the Van and von Mises frequency theory way is still a small n over capital N for in the limit in which the number of trials, capital N, goes to infinity. And this is what has been historically used in scientific work, because, so to say, it's objective in the sense that it's the same for all observers and can be determined in principle to any desired accuracy, provided that you can make a lot of observation, or at least you can simulate a lot of them. And then there is the subjective Bayesian probability, which dates back to the work of Definetti, Ramsey, etc. And this is intimately linked to the belief of the observer. So the probability for an event A is basically a measure of one's belief for A to occur. And this might sound weird to you. How, why is this subjectivity injected here? But it's actually a much more natural way of seeing things. I mean, if we think about our everyday reasoning, every one of us applies Bayesian probability in everyday life. If you ask your friend, I mean, why don't we go tomorrow for a barbecue or a picnic? And you will look at the sky or know that it's in this season and say, oh, tomorrow is likely to be good weather, and so this is your subjective belief about what are the chances tomorrow that you will have a weather that allows you to enjoy a barbecue with friends. So the thing, perhaps, the weirdness comes if you apply such a subjective thing to objective stuff like scientific experiment, but there are ways to do that in a way that is quite rigorous and well accepted, and you will see that. And it's important to note that all the above heuristic definition are obeying the Kolmogorov axioms. So they are all compatible with the mathematical definition of probability, but since they are conceptually different between to each other, they will, you know, if developed, they lead to very differing probability notion and then differing inferences. Okay. So let's see a little bit in more detail what are the consequences of these two, of this divide in definition of probability. So in the frequentist case, the probability is the limiting frequency on independent, identical distributed trials, as you see in this formula here. And sorry for the change of notation. This is what was before small n is now NA. And you have various properties that it's important to actually consolidate in our understanding. So first of all, this definition of probability, this probability use only information from the observed data, okay, and also from the data that could have been observed in other trials. Okay, so both NA and N are the observed data or the data that one can simulate and that could have been observed in other experiments different from ours. This implies that this probability only applies to repeatable events, to things that can be repeated, because you need to repeat the trials to get capital N, okay? So if you are trying to assess in a frequentist way a probability associated to an event that only happened once and is not repeatable, then you are out of tools. You cannot do that because you cannot define for an event that only happens once many trials. And if you cannot define many trials, then you cannot define your successes. And if you don't define your successor and the trials, you do not have a frequentist probability. Okay? So this applies to data because data are random and can be repeated, but it's actually debatable if theories are repeatable. I mean, what is the probability that supersymmetry exists? Well, you know, supersymmetry is a theory, and it's a theory that is valid in our universe, in our nature, perhaps, or it's invalid. But we do not have many repetition of our nature. We only have one nature. We only have one theory. We cannot define capital N. We cannot define a probability for supersymmetry to be true. You know, supersymmetry is either true or not true. There is no a distribution of probability for that, at least in frequentist thinking. And the same thing holds for the barbecue tomorrow. So tomorrow, there is only one April 28, 2022. This is not repeatable. The condition that will be tomorrow are never repeatable, right? There is only one such a day that is April 28, 2022. So what we do in our thinking when we guess if tomorrow there will be the sun or it will rain is actually a generalization. You know, we don't care about the specifics of tomorrow. We just know that usually at the end of April, you know, in Italy, once today is pretty clear, probably tomorrow will be pretty clear too, because spring is coming, etc., etc. So we're making a probabilistic statement not about the very day of tomorrow, but about a generic day at the end of April in the northern hemisphere. I hope I was not too confusing here. So, and another consequence of frequentist definition of probability is that here, the the deduction you can make are restricted are all based on the probability of having some data given the theory. So you try to understand which are the theories that make the observed data more, more frequent, more favored, okay? Instead, in the Bayesian case, here the probability is a subjective degree of belief. And so here the information you're using to assess your probability is not only the information you get from data, as you did in the frequentist case. Of course, you take the model, you take the information from data, but here you also add some information, which is the one coming from your belief, okay? And this is typically called the prior information. So the information that comes from what you know or believe about the problem at hand. And this, of course, since you are injecting more information, you are achieving a more powerful, a more general definition of probability. But the price you pay is that this more general definition of probability may differ depending on the observer, of the operator, of the person that does the inference. Okay? And this, in this probability, you treat as random variable not only the repeatable events, not only the repeatable statistical experiment, but everything. You can assume that the universe is and the physics constants are random variable. Everything is a random variable and can be treated as such, because you can assign to it a probability based on your prior belief. You don't need to be repeatable. And in Bayesian probability, what you get is exactly the backward process that we were talking before. Is you get the probability of a theory given the observed data, which, if you think about it, is exactly what you would like to have for any of your statistical problems, because you observe some data and you want to know what's the probability that my theory is right, or that my neighbor theory is right, etc. So this is the inferential reasoning we will be all interested to, and frequentists give up on this because it doesn't apply to processes that are not repeatable, like theories, but Bayesians use it. And here there are some, some funny, some historical definitions from the very founders of these concepts. Reverend Thomas Bayes in 1763, and Laplace. And then there are some, funny quotes. I don't know from whom. I think I saw them from Louis Lyons, but probably they're from someone else. That frequentists use impeccable logic to deal with an issue of no interest to anyone. And the issue in this case is, what is the theory that makes our data most probable, most favorable? And instead, Bayesians address the question that everyone is interested in by using assumptions that nobody believes. So these are two paradoxical things that somehow enhance the limitation of each of the two approaches. So while I myself am biased toward the frequentist interpretation, because I'm just comfortable with that, in the lectures I will try to give you a fair representation of both schools, and then you will choose whatever makes you more comfortable. But the important thing is that every practitioner understands to a certain degree the limitation and the shortcomings of either approach. And so you can, you know what you're doing when you do your own measurement, or you know how to interpret when you read someone else's work. you know, in the case that it's frequentist or Bayesian, it doesn't matter. You should be able to understand it and also understand the pitfalls event. So let's talk a little bit about an important concept, which is, you know, somewhat disregarded, and it's important because it can change the meaning of probability. And this is the so-called sample space. So for any probability to be well defined, you need to define very well what is the whole space. So what is the set of all the possible outcomes of your statistical experiment? And perhaps there is no better way of conveying this concept that using the tweaking of that concept that some marketing campaign do. You might have seen in some, you know, airline marketing, the sentences like, you know, 90% of our flights arrive on time. And then you compare this with your personal experience and say, no, it doesn't happen. You know, I'm late much more frequently than 90%, than 10% of the times. And this is because, you know, they are cheating you, no? The flight that are delayed for several hours are usually canceled. And so once they get canceled, they do not belong to the sample space of the flights anymore. They're not delayed, and so they get excluded from the sample space. And so this makes the fraction of flights that are in time artificially higher, and so it makes the airline to look better than it is. Or you know, a few years ago, there was this things you get in the magazine to say, you know, try this diet. Our survey shows that most people lose 5 kilograms in a month on this. And this, you know, their survey was that happy customer who did the diet seriously and lost weight were more likely to answer the survey, where the disgruntled ones who did not get any benefit from the diet, when they got the survey, they just, you know, throw it in the garbage. And so, you know, the answers are biased toward a positive outcome. So, I mean, this is all to say that whenever a probability discussion, statistics discussion is ongoing, you should make sure that all the involved parties are agreeing on what is the sample space. So now we're going to go. Let me check if there is anything on the chat, or no. Okay. So now we're going to go to the Bayesian inference first, because that's you know, quote unquote easier, and then we will deal with the frequentist inference. So to start with Bayesian inference, we should define the important concept of conditional probability in order to then introduce the bias theorem. So the conditional probability is written in this way here on top left, is probability P of event A given that B has occurred. Okay, so given that is this vertical bar, and it conditions your statement to the occurrence of event B. Okay, so what we're actually doing here is to restricting the sample space omega that before included all possible outcome. In this statement, we are restricting it to just the subset B. Okay, so if I write P of A given B, so P of A conditional to the occurrence of B, I'm effectively saying that B has become the new sample space. Okay, so if the outcome is in A, then the outcome is in the intersection between A and B, because B is my total sample space. Then if the outcome is in A, I have the intersection of A and B. And since the maximum value of the probability of A and B can only be the probability of B, because B is my sample space. It doesn't get better than that, right? I mean, that's the maximum you can get, the whole sample space. Then the conditional probability is written as you see here. So P of A given B is equal to the probability of A and B divided by the probability of B, which is a normalization to the whole sample space. In this case, the whole sample space is only B because I'm talking about conditional to B. And so if you reverse this, the probability of obtaining A and B is equal to the conditional probability of A given B multiplied by the probability of B. Okay? This is very simple, logic. There is nothing difficult here, I hope. But of course, if you have questions or if you're unclear, ask. So you remember at the beginning yesterday, we mentioned about joint probability, conditional probability, marginal probability. So this is coming back here, right? The P of A and B is the probability that A and B occur jointly. So that's the joint probability of A and B. And this can always be represented as the product of the conditional probability that A occurs given that B has occurred times the marginal probability that B occurs. And this is, summarized here and can be written both ways, right? You can write in terms of the probability of A given B here on the top row, or you can write it in terms of the probability of B given A in the bottom row. You just multiply for a different marginal, P of B in the top row, P of A in the bottom row. And now, I mean, if you agree that these things are true, you have all the ingredients to understand the Bayes theorem. The Bayes theorem is actually a key relation between the conditional and marginal probabilities, and it's the relation that I just told you a second ago. So P of B is equal to A given B times P of B divided by P of A, because you are equating these two rows, and therefore you have an expression of marginal and conditional probabilities, a relation between marginal and conditional probability. So then there is some language, some lingo here. P of B given A, it's typically called the posterior probability because P of B is evaluated after fixing a specific value of A. And then if you take P of B given A as a posterior, P of A given B is the conditional probability of A given B, and which you multiply by P of B, which is called the prior probability, because is evaluated before, so prior to knowing any information about A. Okay, so this is a mathematical theorem, and of course it's valid. It's pretty intuitive if once you understand the concept of conditional and marginal, it's pretty intuitive, and there is no way that this is not valid. The Bayes theorem is valid, and everybody believes that. One nice way of convincing itself that the theorem is valid is to look at these sketches here. So you have to refer to this, top left picture where you have the whole space, which is a rectangular shape, And in this whole space, you are selecting two partially intersecting set of outcomes, A and B, okay? So if you try to represent graphically what the different ingredients are, you can have these nice pictures to the right. So if you look at P of A, you have this vertical ellipse over the big rectangle. If you look at P of B given A, that's the area of the horizontal ellipse over the rectangle. If you look at the probability of A given B, you're restricting your sample space to B, you remember. So at the denominator, you no longer have the rectangle, but you have the horizontal ellipse. And at the numerator, you get just the small fraction of A that belongs to the horizontal ellipse of B. So you have this small thing there. And same thing with P of B over A. The numerator is the same because this is the interception, but the denominator, so the sample space, is different because in that case is the vertical ellipse that represents the A set. And then if you look at the intersection, what's P of A and B, you're getting this small, piece at the numerator over the whole sample space. And so if you try to work the two relationships between marginal and conditional probability that I just introduced in my previous slides, you will see that they work very well, even with this somehow graphical representation, because in this top, these two final rows, you can see that you can simplify the vertical ellipse and you get the intersection. And in the second and last row, you get that you simplify in the product the two horizontal ellipses and you get the same thing. Now here there is an important concept to remember. And you have to really ensure that you understand that P of A given B is not equal to P of B given A. These two probabilities are different. And probably one of the most effective way of remembering that is that if you take as random variable A the fact of being pregnant or not pregnant, and if you take as random variable B the gender, male or female, you will immediately realize that P of A given B is not equal to P of B given A, because the probability of being pregnant, given that you are a female, I mean, it varies across countries, etc., but you can take it as a few percent, maybe 3%. But of course, the probability of being a female, if you are pregnant, given conditional to the fact of being pregnant, is of course much higher than 3%. Okay, I hope that makes it clear. So we just learned this nice bias theorem, and the bias theorem is very powerful if you're only dealing with random variables. So if both X, the data, and M, the parameter we're trying to estimate, are random variables, and you have a model for them, P of X given M, where X is the data you observe and M is the parameter you want to estimate, then you can certainly use the bias theorem and you will have the most complete and precise inference you can get. Because you observe X, so you perform a measurement of X, and you want to say something about M, and so you rewrite the bias theorem, what before we wrote in terms of A and B, here can be written in terms of X and M, and you get the posterior probability for the parameter M. So P of M given X here at the center of the formula, P of M given X is basically your model P of X given M multiplied by the prior P of M and normalized. So if you're dealing with random variables, not only in the data are always random variables, but also in the parameters you're trying to estimate, then the Bayes theorem is the best way to go, provided that you know the prior for M, of course. So let's see an elementary example of this, just to fix our ideas. Suppose that we have 3 identical bags, okay? And in each bag there are 2 balls. And the balls can be black or white, okay? And in bag A, we have 2 white balls. In bag C, we have 2 black balls. And in bag B, we have 1 white and 1 black, okay? And now suppose that I do my statistical experiment and I want to do my inference. I pick a ball randomly from one random bag. I don't know which bag is A, which bag is B, which bag is C. I pick a random ball, sorry, I pick a random bag, M, which is unobservable because I don't know, and a random ball inside it, which is X, is the observable, because once I pick the ball, I look up at which color is it, and I try to infer whether the bag I used to pick my ball was of type A, of type B, or of type C, okay? So I'm trying to infer the label of the bag from the color of the ball. So in this case, X, the data, is the color of the ball, and M, the unknown parameter, is the label of the bag. So I pick this ball and I see that it's white, okay? So what can I say about the chosen bag? What I want to know is the probability of M given X. So the probability of bag A given that I observed white, and the probability of bag B given that I observed white. And I also want the probability of bag C given that the observation is of a white ball. So if I write the probabilities here, I will have that the 3 bags are identical, and so I have my prior for picking either one of them is 1/3. So P of M here is 1/3. I have 1/3 chances to pick bag A, 1/3 chances to pick bag B, and 1/3 chances to pick bag C, right? And then within each bag, I can, you know, evaluate. I can determine the probability of observing a white ball. So in bag A, this probability is 1 because bag A has only white balls in. In bag B, the probability of picking a white ball is half because we have 1 white and 1 black. And in bag C, the probability is 0. Okay? And therefore, I have now all the ingredients to calculate what I want to know, which are the posterior probabilities, okay? If I, you know, work out the simple algebra here, I get that the posterior probabilities are P of bag A given that I observed white is 66%, P of bag B given that I observed white is 33%, and P of bag C given that I observed white is 0. And of course, you know, you don't need the Bayes theorem to guess this, But I think this is a nice and simple example that shows you how you are supposed to work once you're dealing with two random variables, which are in this case the color of a ball and the label of a bag. Is that clear?
Can I ask something here?
Sure.
How did you estimate P of W here?
Because you know that P of W given M, you mean? This first line.
No, just P of W. Because you don't know like whether there are equal number of white or black balls, right?
Yes, that you know.
Oh, okay.
You know, someone told you that bag A have two white balls, bag B has one white and one black, bag C have two blacks. What you don't know is, once you pick a bag, what you don't know is which bag is that, if it's of class A, class B, or class C. But you know the content of class A, class B, and class C. Is that clear?
Yeah, sorry, thanks. Yeah.
Okay. So this simple example was meant to convey the idea, the concept that in Bayesian inference, the posterior density says it all. I mean, if you manage to build and to determine your posterior probability density, you have all you can possibly desire to have the best inference. What is this posterior density? Well, in the previous example, the posterior density is discrete. You see, it's P of A given W, P of B given W, P of C given W, so it's an histogram. But in many problems, it's just a distribution. It's a distribution of, in the vertical axis, you have P of parameter given data, so that's the posterior, and then the horizontal axis, you have the parameter. So you are assigning a posterior probability to any value of your unknown parameter, or the parameter you're trying to infer. And once you have constructed this posterior probability, then you can do whatever you want. You can take the mean of this distribution, and the mean of this distribution offers you an estimate of the central value of the parameters that minimizes its variance. Or you can take the highest value, the peak, the value of M where this distribution peak, to get the highest posterior density as the most probable value. But remember what we said yesterday, right? That the mode of a distribution is just a matter of the matrix. So you change the matrix and the mode changes. Or you can take an interval here. You can decide to say that your M value is contained in a 95% here in the top, a 95% probability interval, for instance, from here 0.55 to 0. Whatever 92 or something. Okay, so once you have the posterior density, you have everything you may possibly want, and you will be able to give a very informative inference. And it's important to know that frequentists too believe, of course, and use the Bayes theorem. The Bayes theorem is a mathematical theorem, it's not a philosophical thing. So frequentist statisticians too use Bayesian statistics when it applies to random variables and when the prior distributions are known. The prior, remember, the priors are this P of M, right? because it would be stupid not to be so and not to do so. Once you know the priors, the best thing you can possibly do is to use Bayesian statistics, and this happens every day in medicine, biology, in many of the human natural sciences actually. So there is no divide between frequentist and Bayesian statisticians at this stage. If you know the priors, it means that you're dealing with random variables both in data X and in parameter M. Then there is no point in doing else than Bayes theorem. Oh, I have a question in the chat. Let me check that. Yes, that's a good question. There is arbitrariness. If you're looking at, if you're setting a range, a 95% confidence, not confidence, credibility in this case range, or a 90% range, you can set arbitrarily the limit, the boundaries of this range. And you can try to make it the shortest possible. So you start from the peak and you start accumulating posterior probability to the left and to the right until it's shortest. But you can also take one side or the other side. So there is an arbitrariness. Does this answer your question?
Okay, but then suppose one person's result will not match with another one. The way we choose the range, that will vary. Yeah,
but that's not a problem. Once you're writing in your paper that you have determined a 95% credibility level range for your parameter, it's understood that there is 5% of the value of your parameter that will not belong to that range. And if someone else has a different range, his or hers 5% would be a different one. It's not a problem. The results are still compatible, even if there are different choices of the boundaries of the range.
Okay, so I think with that we should also write the rule that we choose to have that range for 95%.
No, it's not needed. It's it's when you write your paper to distribute your result publicly, it's usually good to say which criterion you use to determine the boundaries of your range. So you say this is a 95% credibility range chosen such as to make it the shortest possible. But depending on the physics problem you are dealing with, sometimes you might prefer to have a larger range, but that excludes a region of the parameter space that is more relevant for providing more important physics information. You just write which criterion you use and you're fine. It's not incompatible with other ranges.
Okay.
Any other questions? Since we are at it. All right. So let me go back to the full screen thing. How do I get? I have the chat in the middle, sorry. So once you're applying your statistical experiments to random variables that are not only the data, but also the parameters, and you know the priors, you get the backward process probability through the Bayes theorem, and you use that, no question about it. The problem and the divide where the two schools part is, what do you do if priors are not known, all right? Or even worse, what do you do when priors cannot be defined because, for instance, your parameter M in frequentist theory is not something that can be repeated. So suppose that, you know, M, the parameter you're trying to determine is the value of a physical constant, say the speed of light or the Higgs mass or whatever. Philosophically, some of us may be in difficulty in thinking that a physical constant has a probability distribution. You know, for instance, I myself tend to think about that, and maybe it's just my mental representation, don't pretend it to be the reality, but I think of that like a physics has a value that nature gave it to it. We don't know exactly this value. We probably never know it exactly, of course, but it has a value. So it's specific value. So its probability distribution will be basically zero everywhere, except of a Dirac delta centered at the value it has. Okay. So it's not a random variable. It's not something that can change. There is only one nature. There's only one speed of light. And at least if you leave apart the multiverse interpretation of cosmology, etc. But let's not diverge here. And in this case, physical constant cannot be interpreted as a repeatable thing, and therefore you cannot assign a probability to that, and therefore you cannot even assign a prior to that, and so you cannot use the Bayes theorem to any inference about that parameter. Okay. So the difference, the two schools part here, because frequentists, when they are dealing with parameters to which they do not feel comfortable in assigning a probability distribution, they give up the idea of getting P of M given X, so P of the parameter given the data. So they give up the idea of the backward process explicitly expressed by the parameter, by the probability of a parameter given the data. And so they revert, they make a step back and they say, oh, I don't know, this is not a random variable, I cannot define priors, I don't know them. Let me make a step back and revert my estimate basing only on the assumed model. And giving up on using any subjective prior knowledge. Instead, the Bayesian school, they say, let's stick to the Bayes theorem and assume some priors. Even if we do not know them, assume them, because for the Bayesian, everything is a random variable. Okay? Everything, physical constant, 28 April 2022, the existence of God, etc., etc. Everything is a random variable, so everything can be assigned a prior. And if you don't know it, you can assume it. Okay? Of course, in physical sciences, and especially in high energy physics, the Bayesians also, even if they assume priors, they try to set up their priors in a way in which they do not completely determine the inference, because Bayesian physicists, they still know that what we're interested in is what the data tell us, not what the prior tell us. So if you have data and inject a very informative prior that completely moves your inference, you are not doing a very good service to your community, because some other physicists who may use a different priors may get a completely different result. So they try to use priors that have minimal influence in the result. But still, they do have an inference, because it's statistical information that is injected into the inference. So it cannot be completely inconsequential. And those of you who may have touched upon these topics may have seen that there is an ubiquitous usage of, let's call so-called uniform priors or flat priors. They are commonplace, unfortunately, in many papers, many HAP papers, and they're based on the, I think, fallacious intuition that knowing nothing about a physics parameter, like speed of light, you don't know nothing about the prior. So if you assign a flat prior, so you assign equal probabilities to all the possible values, you are making a Bayesian inference that is objective, that has no influence from the prior. And this sounds intuitively plausible and has attractive practical features, but unfortunately is wrong in the sense that it's, even if you assume a flat prior, you are injecting information and you are injecting your own subjective, bias into the inference. And here is where I try to recall what we said yesterday. You remember that any distribution with an adequate change of variable can be transformed into a uniform distribution. Remember the probability integral transform? That's exactly the case here. When you assume a uniform prior, all you're doing is just choosing a specific metric where your probability distribution is uniform. But if you change the metric, that thing that was uniform in this problem will be not uniform. And so that's this dependence somehow on the metric introduces, an arbitrariness that should make it clear that the uniform priors are not uninformative. They're actually quite informative. And of course, Bayesian statisticians figured out this problem various years ago, and they try to find what are sets of priors that do not actually inject information in the problem. And Jeffries, worked on that problem for a long time, and he found actually some powerful choices, especially in one dimension. But of course, it becomes much more difficult when your inference is multidimensional. So in the end, it doesn't solve the issue at all. A better approach is perhaps, instead of trying to find a prior that does not inject subjective information, which is probably impossible, and maybe it's also violating the very Bayesian philosophy because you're supposed to inject information there. A better approach, someone that is favored by both frequentist and Bayesian, when you do a Bayesian measurement, you do it and you try what would be the change in your result depending on the choice of the prior. So you determine your result with your default choice of the prior, and then you repeat the determination with variations of your choices of priors. And if you see that the results are approximately stable, then you have a valid evidence that the information that the prior is injecting is very limited. And so the inference is pretty objective. If you see that your results vary wildly, depending on the prior you choose, it means that you're not measuring the data. You're just, you're just injecting information and getting it back under the form of the results. And this example here from a paper about 10 years ago is exactly that. You see, you have a column where a table with a column with a choice of priors. So you have default, flat in this, flat in that, previous together, flat in amplitude. And you see on the second column how the result change. And you see that the changes in the result, so the results here are expressed as intervals, not as center values, but it doesn't matter. And the changes of the results are modest, which means that, in this case, the choice of prior was not completely spoiling the information from the data. And this is a very nice and useful calibration of any Bayesian result. Okay, I think this is probably good to make a short pause because we are already 1 hour and 5 minutes into our lecture. I'm gonna get a glass of water and come back in a minute.
Okay, thank you, Diego. Yeah, just pause for a couple of minutes.
Okay, so if you have questions, maybe this is a natural chance.
Hi, Diego. A quick question.
Yes, please.
In just the slide before this, when you were discussing about flat priors, you had a statement with the second para. You specifically said in one dimension. So I didn't understand why this one dimension was emphasized.
Yeah. One of the reasons why uniform priors are so popular is that in one dimension, a Bayesian inference based on the uniform prior and the frequentist inference based on maximum likelihood give the same results.
Okay.
So people tend to find this as reassuring, you know, and so they use uniform priors, but unfortunately they use also in many dimensions. This is no longer true. This you know, correspondence between frequentist and Bayesian is an accident that only happens in one dimension.
Okay, thanks.
I think Gagan wanted to ask.
Yeah. Can you hear me?
Sure.
Okay. Sorry. So maybe a very stupid question. If you go to slide number 13, where you are showing that very interesting the product part, and I was kind of, you know, it's a really very nice way of introducing to the students. So very likely I will use it. I hope you don't mind the copyright if I take it. So the point.
I myself stole it from Bob.
Okay, fine. All right. So the question I have is that expression, you have this PA multiplied by P, you know, that where you're getting the intersection, correct, that penultimate line. So I'm looking at the picture now. Now, if I look at the denominator, the picture, the product of the denominator, so you have the big rectangle versus the egg, you know, that ellipse. There I get the end result to be the big rectangle. Now I am doing the same thing for the numerator. You have the egg and the intersection small region, sort of 1/4, 1/8 of big egg. So that product becomes the B quarter, you know, whatever 1/8. Just wondering if I miss somehow here that that product, how exact. Oh, it get canceled out. I'm so sorry. Okay. The egg from numerator denominator get canceled. Sorry. Okay.
Yeah. You have to. I don't know how you multiply. I don't know.
No. Okay. Get it.
I assume that you can simplify these guys and these guys, and you get this.
Right. Sorry. Yeah. Okay. Got it.
Okay. if there are no more questions, if there are other questions, please ask. Otherwise, we can probably continue. All right, I don't see any. So let me give you the full screen again. Okay. So we were here. Yeah, yes. So I just said that if X and M are random variables, then everybody is happy and looks and uses the Bayesian thing. If M is not a random variable, then the Bayesians keep using the Bayesian theorem, assuming priors. And then here the natural question is what does the frequencies do? So what can I compute without priors? Certainly I cannot compute P of M given X. I cannot compute the probability of physics given the data because I do not have the priors, and I do not think that, you know, conceptually I can assign a probability to something that is only valid once, which is a physics constant or a physics theory, etc. So what the frequencies do is actually to use the model. You remember P of X given M, use the model to favor or disfavor a certain theory based on how likely is that this theory generates the data that I observe. Okay, I will try to, you know, consolidate this a bit in the next few slides. So here we are introducing the concept of likelihood. And the likelihood is a mathematical function, L, which is a function of the physics parameter, M. And the likelihood is basically a way of looking at the model of P of X given M in a way that is parametric to the data observed, X0, and is function of the parameter M. So here you see that there is some kind of ambivalence in interpreting what the model is, right? Because if you take the model P of X given M and you fix M at a specific value, for instance, M prime, so you fix the physics parameter at a specific value, then the model P of X given M prime becomes the probability density function of observing generic data X. So in this case, the model P of X given M is a function of the data, is a function of X. But you can reverse this picture and you can take the data you observe as fixed, okay? And you fix them at X0. And if you do that, then the model P of X given M becomes just a function of the physics parameter M. And we call it L of M. You see here in the second bullet. So the model seen as a function of the physics parameter at given data, at fixed data, is called the likelihood function of the M parameter. So the likelihood is called a likelihood because it's not a probability. So remember that likelihood is not a probability. However, it is connected to the probability of observing data X for each choice of the parameter M. So the likelihood expresses the probability of observing the data for each possible choice of the parameter M. If nature put the speed of light here, then I would observe this set of data of my experiment. If nature had put the speed of light there, then I would observe this other set of parameters, etc., etc., etc. Remember that this is not the probability of M. This is not the probability that M has some value given the data, because that is the prior. And we're not dealing with the prior, we're dealing with the likelihood. Okay? And we do not assign probabilities to things that are not repeatable. And since in this case, the theory and the parameters of the theory M are not repeatable, we cannot assign a probability to them. All we do is to assign a probability to the data given some choices of possible M's. I know it's a little bit confusing, but I'm sure that if you stare at this and think a bit, you might catch it if you have never seen it before. So the likelihood is a complete summary of the data relevant to the estimates at N, is a very powerful instrument, and ideally one should publish the whole likelihood itself. And there is actually an effort in HEP toward going into this direction, because that would be a very, very good way of making our measurement long-lasting and more complete. And another important thing, and we will get back later, is that the likelihood, that is the model, is the single strongest driver of inference. So sometimes when you're working to a statistical problem, a data analysis, whatever, you name it, people get very enthusiastic about, the minimization here, there's, advanced tool one uses there, but all of these are actually details that have very, very little influence on the final result. If you really want to influence your final result, you have to improve your model. You have to get a better likelihood, a likelihood that represents the complexity of the data in their full articulation, okay? So, to summarize, the likelihood is an interpretation of the model P of X given M, where data is fixed and the model is only function of the physics parameter M. So you have to remind that a likelihood, even if the mathematical form is the same, a likelihood is not a probability density function, because the probability density function P of X given M is a parametric function of the observable X. So this is a function of observable X. If you plot it, you have X on the horizontal axis. The likelihood function L is instead a function of the parameter M. So if you plot it, you have M on the horizontal axis. And another way to see that is that the PDF, which is probability density of the data, should be normalized to unity. So if you do the integral of your model in the matrix of X, dx, you should get 1, because all the possible outcomes should be there. But the integral of the likelihood has no meaning. It is arbitrary, it can be anything, okay? And in addition, and that's important, the maximum of the likelihood, so the value of M that maximizes the likelihood, is invariant under reparametrization. So if you have if M hat is a maximum likelihood estimator of M, then if you have a function of M called f of M hat will be a maximum likelihood estimator of that function. So let's see what the actual likelihood means. Let me plug it the phone, otherwise you will lose my image in a short time. Okay. So what does the likelihood mean? The likelihood expresses the probability of observing the data you observed as a function of the parameter M. So if you have done your measurement, that means you have a set of data x0, there will be some possible values of the physics parameter m you're interested to, that if plugged into the likelihood will give you a small number. So the likelihood of your data for those values of the parameter will be small values. This means that it is unlikely for nature to generate that set of data if the true parameter of m in nature would be that probe value m that I'm trying. Conversely, values of m that make your likelihood function large are favored. It means that it would be likely for nature to generate the data you observed if the m value in nature would be that probe value m high. It is important that it is clear. So if it's not clear, please feel free to stop me and we iterate on that.
So Diego,
Yes.
So is it always then preferable not to write L of m, but L of m given x naught?
Oh, there is, you know, there is a whole variety of notation here, and I myself probably changed a couple of times during the same lecture. So yes, whatever makes things and for your audience, it's good. And yes, if you write in this way, perhaps it's clearer that likelihood is a function of m, conditional to the data that are observed. But you can really find any wild notation in this business. So I myself didn't manage to converge on something consistent throughout. It's important though to note that if you change the data, if you do another observation, or if your colleague does another observation, the likelihood will change. Because instead of being L of m given x0, it will be L of m given x1. And since x1 is generally different from m0, from x0, you will get a different likelihood. Okay? So a likelihood somehow is a random variable. It changes with different observations. Okay? Oh, yes, I wanted to say that the value of m that maximizes the likelihood is not to be interpreted as the most likely value of m. Okay? This is conceptually wrong. The value of m that maximizes the likelihood is the value of m that makes your data most likely. And then there is, a technical point at the end that since physics usually deals with repeated observations that are independent and identically distributed, then the likelihood for a single observation is L of m, then the likelihood for independent and identical observation is the product of the single event likelihoods. So why do we insist on the likelihood concept? Well, we insist on that because the likelihood-based estimates have very desirable statistical properties, and probably they are your default solution for in most of the inferences you will either have to do or you will read on papers. The maximum likelihood estimator is basically the value of the parameter you get that maximizes the likelihood given your data, and under pretty weak condition and in the asymptotic regime, so for infinite observations, which is an idealization, of course, has very nice properties. So first of all, it is consistent. So it converges in probability to the true value. And I'm not going to write here the mathematical definition of convergence in probability. I just write here as little sketches that provide the concept, where you see that for increasing number of observation, you know, the maximum likelihood distribution shrinks and converges to the true value M0 in this case. Another important property is that the maximum likelihood estimator is efficient, which is a technical way to say it's the most precise possible. It has the minimal variance among all the estimators. And even more important is that for, you know, very large number of observation, the maximum likelihood estimator has known distribution, which is Gaussian. Okay? And then it's also reparameterization invariant, which I already mentioned. Okay? So it's consistent, it's precise, and I know its distribution. That's great, right? But unfortunately, this only happens for infinite observation. And of course, we never get infinite observation, but in some statistical problem, we get observation numerous enough to be approaching this asymptotic regime where we can assume observation almost infinite. In many other problems, this does not happen. And so some of the mistakes that you usually find in physics papers that are dealing with maximum likelihood estimator is when people assume that those properties hold, but in fact, the likelihood of their problem is not yet in asymptotic regime. So it's very important to check when you're doing a maximum likelihood estimate that you are in a regime where these properties can be valid approximately. And if you're not, you have to work out with simulation the actual properties of your maximum likelihood estimator. And even if you're in a asymptotic regime, the likelihood still also is not perfect. I mean, first of all, it's a biased estimator. It's known to be biased. And fortunately, the bias shrinks with an increasing number of observations, but it's still there. And another important element here is that the maximum likelihood estimator does not provide any goodness of fit information. Okay? So if you are having a completely wrong model and you maximize your likelihood using that model, you will still find a maximum, you will still quote your determination of a physics parameter M, but there will be no point, no procedure to tell whether that your model is wrong. And so there is no way of understanding whether your fit is good or not. Okay? So let's do some example to try to fix in our head what is this maximum likelihood business. Take a decay process, assume an exponential model. Okay, so we all know that the P of X given M, which I wrote here as P of T given tau, is actually, sorry, apparently didn't work. Just give me a second, I'm trying to see why it doesn't work. Or maybe you're gonna lose my image in a while. I don't know why it's not working, my charger, but I hope it's not a big deal. So in an exponential problem, you have P of X given M, the model is known, right? It's written here, it's a decreasing exponential normalized to tau, right? As the probability density is known. So if in your experiment, you observe a set of n decay times for a number of particles, and you try to infer the lifetime, all you do is that you write your likelihood and maximize it, okay? So the single event likelihood, so if you have only one particle, one decay, you write this. Your likelihood is a function of tau, so it's function of the physics parameter, and it's the model evaluated at the data you observe, t with k, because you only have one observation, one decay time measured. And so you replace t with k in this PDF and you get your likelihood for a single event. But you do not know, you do not make only one observation, make many of them. And so since these are identical and independent, you can multiply the single event likelihoods among themselves, and you get this last line here where the total likelihoods is the product over the observations, which are n, over of the single event likelihoods. Then you work out the algebra and you get this expression, okay? So since you want to maximize this expression, you set to 0 the derivative and try to find what is the value tau hat that maximizes your likelihood. And you will see easily that the value that maximizes your likelihood is actually, in this case, the average, of the observed decay times. So tau hat is the sum of tks over n. Okay, so you have found the maximum likelihood estimate of the decay time of the process you are interested in. Note that if you had framed your inference in terms of the natural weight gamma, so 1 over tau, you would have found the same thing, because L is invariant under parameter transformation. So its maximum is so too, and it's expressed in this last line here. Let's look at another simple example, a textbook example, just to fix the difference between a likelihood and PDF. So suppose that you have a Poisson distributed signal where there is no background, and therefore, the PDF is a Poisson where J is the data you observe, so the counts you have in your data, and mu is the rate you want to estimate, okay? So P of J given mu here on the top is the usual Poisson formula, and it can be interpreted as a function of mu only as the likelihood of your problem. And so here you see the difference, right? On the left, you have the PDF, which is a discrete function of the data, mu to the j over j factorial times e to the minus mu. And this is the PDF. So this is function of the data, j. J here is what I call x so far, is the data. Instead of on the right box, you have the likelihood, which is a function of mu at given data. So at, for instance, a number of counts 5, and this is mu to the 5 over 5 factorial e to the minus mu. To the left, the PDF is a discrete function of data j. To the right, the likelihood is a continuous function of the physics parameter mu. So also here, I minimize or I maximize my likelihood, therefore I minimize my negative logarithm of the likelihood. This is a useful and popular, mathematical artifact. And you get that the maximum likelihood estimate for mu is mu hat, and it's equal to the observed number of count, j. So if you have observed 5, then your maximum likelihood estimate is that mu is equal to 5. So what happens when you maximize the likelihood? Well, this is a picture, I hope it helps. You have an observed value, j equal 5, and then you want to maximize the likelihood given those data. So suppose that you do it by trial and error, and you try, what is the likelihood for my data if mu is equal 0.5, I get a very small likelihood, you see here in the picture. What is the likelihood if I try mu equal 5? It's much better, right? It's pretty high. What is the likelihood if I try mu equal 20? It's again low. So I've crossed my maximum most probably. And in fact, if I plot my likelihood as a function of mu, as it's appropriate, I will see that it peaks at 5. I hope it's all clear, but please tell me if it's not. I don't see the chat, nothing in the chat. Okay. So by maximizing the likelihood, we have an estimate or a so-called best fit of our parameter. But we all know that we cannot get away only with that. We also need to set an uncertainty for that, right? Every experimental determination is accompanied by uncertainties. So how I get the uncertainty? Well, the uncertainty depends on the estimator's variance. So the maximum likelihood, which is my estimator in this case, is a value that depends on the data I'm observing. If my colleagues is dealing with a different set of data, then her maximum likelihood value will probably be different from mine. And then I have another colleague who does the same thing, and he also gets a different value, and then another one, and she also gets a different value, and blah, blah, blah. And so if you put all your maximum likelihoods that all of these colleagues find in a distribution, you will have a distribution. And the spread of this is a measure of your statistical uncertainty. So in this picture here, I put myself in the ideal case, asymptotic case, in which the distribution is Gaussian. And you will see that, all of these colleagues doing all the same measurement will have populated the distribution with their results. And then 68.3 of the results would be, within 1 sigma from the top, and then 95.5, 2 sigma, et cetera, et cetera, et cetera. Okay? So this is the theory, right? So how do I get from one only observation? If I'm doing only one experiment and I don't have all of these colleagues helping me to form this distribution, how can I get an estimate of the uncertainty? Well, one thing is to try an analytic calculation. You remember, you are looking at the standard deviation, so you calculate the variance, as we saw in the first slide yesterday. The maximum likelihood estimate is a function of the data. So m hat is a function of x. So I can calculate here, you see, in the middle of my slide, you see I can calculate the expectation value of the maximum likelihood estimate minus the expectation value itself to the square, and hoping that I know my model analytically and that the integrals are tractable, I can calculate that analytically. So as you probably imagine, this is only possible in very few textbook problems, but I've never seen that happening in a real physics measurement. So in a physics measurement, there are two ways of getting away with that. One is to approximate the uncertainty with its ideal lower limit that fortunately is typically known in a maximum likelihood estimate. And whenever this is not possible, you have to get it brute force from simulation, which means that if you do not have all of these colleagues helping you doing the same measurement as you did, you can simulate them with a computer. So let's see the first way. The first way is, I mean, this is a little bit technical, and I don't pretend to explain you the mathematical details here. But in the likelihood theory, there is a very important quantity that is called the Fisher information. And the Fisher information is a measure of the information carried by an observable over a parameter m connected with a model P of x over m. And this is expressed here. And the important thing for our scope is that the Fisher information gives us a way of estimating the variance of my estimator, so of my maximum likelihood thing, so estimated actually the uncertainty of my measurement, by using this formula here. So the second derivative of, so the curvature basically of the likelihood at the maximum is in asymptotic condition, so with infinite observation, a good approximation of the uncertainty that I get on my measurement. And so even if I don't have my colleagues helping me, if I don't have a simulation helping me, I can use this mathematical trick here, is mathematical derivative, and approximate the uncertainty that I get. And this is what a usual likelihood maximization programs like Minuit use when you do a fit and you get a result. This is usually done based on that. You know, the curvature of the likelihood at the minimum, at the maximum. Unfortunately, this is not universally applicable. It only works for problems where the likelihood is reasonably Gaussian, and you have no guarantee that your likelihood is Gaussian unless you do the simulation and check it. So you're doing an ansatz here. You're assuming that your likelihood has certain properties and you trust them, which is not wrong. I mean, provided you write it in your scientific document accompanying the result. If you give your peers all the information to form an opinion on how thorough and careful your estimate was, even if you make an approximation and you state it, it's fine. The other and probably best way is to actually use simulated experiments to repeat, to somehow mimic repetition of your measurement, so as to get the real distribution of the maximum likelihood estimate, and therefore a solid estimate of its spread, which is the uncertainty of your measurement. So what you do here, you choose a plausible true value of the relevant parameter, you feed it into your likelihood, and you use this likelihood to draw randomly several sets of simulated data X, which are distributed according to the model. So you have 1,000 sets of 1,000 copies of your experiment, and in each you maximize the likelihood, and you have a distribution of your results, a distribution of your maximum likelihood estimators. And you do that for various values of the true value. This is important. You do not only do it for one choice of M, you do it for various choices of M. And therefore, you know what is the spread of your estimator. And therefore, you know what is the statistical uncertainty of your measure. And one standard way of representing that, which you see everywhere in for instance, in Belle II, but also in other experiments, is that you do this exercise and then you represent the results of your measurements into a pool plot. So this is one of such plots where you have a distribution of the results of your fit, so a distribution of the maximum likelihood estimator, subtracted, so shifted by the true value, which you know because this is Monte Carlo. So you basically know what is what was the true value, and you divided this difference by the uncertainty provided by the fit, which is called sigma fit here. And you see a lot of things here. So you have this distribution, which looks reasonably Gaussian, and that's good. It means that your likelihood is already approaching asymptotic regime. And you also see that the difference between your fit results and your true value is approximately centered at 0, which means that the bias of your estimator is not big. There is maybe a hint here. You see 0.08 plus or minus 0.04, but it's still 2 sigma, so it's not significant. And you also see something else. You see that the width of this Gaussian is compatible with 1, which means that the spread of your fit result is of similar size of the estimate of your uncertainty given by your fit. So your curvature of the likelihood at the maximum, which is basically this sigma fit that you are dividing your difference for, is a good approximation for the actual spread of the result. If it weren't, then you would have either a much narrower or a much wider than 1 fit here. Is that clear? Are you familiar with pools? Perhaps some of you have already seen those. I get silence, so I get everything is clear. And here is reinforcing what is the interpretation of the statistical uncertainty. So it's the square root of the variance of the estimator, and it's called typically sigma. And usually a result is quoted as m hat plus or minus sigma. What does it mean? It means that you rewrote this in terms of intervals. So m hat, so your maximum likelihood estimator, minus sigma, and the interval that has as bounds m hat minus sigma and m hat plus sigma include the true value of the parameter as 68%, with 68% probability. So this is typically the way that people interpret your result when you give an uncertainty. If your estimator is unbiased and your statistical uncertainties are, properly evaluated, people expect that your result expressed as an interval includes, or in other words, covers the true value of m with 68.3 probability. What does it mean? It means that if you repeat the measurement 100 times, about 70 times, the true value will be included in the interval you get, in the results you get. And this is, I'm trying to express this in this picture here on the right, where actually the intervals that you get from 20 measurements are those horizontal lines, and the true value m is this vertical line. And those intervals are actually not 1 sigma interval, they are 2 sigma interval. And you see that, the intervals fluctuate from measurement to measurement. So all the horizontal lines are not all aligned. They go left and right because these are function of the data, and therefore they fluctuate depending on the data you have. But what is important is that 95 of them cover, so include the true value. You see that only 1 out of 20 intervals here at about 6 in the simulation number, it's not including the true value, okay? And this thing is called coverage, and it's a very important property. It's the capability for an inference procedure to yield uncertainties. So the capability for an inference procedure to return uncertainties that cover the true value with a stated confidence level is a fundamental requirement in frequentist inference. It's a very important business. And why is that important? It's important because it ensures that the communication of our results to our peers is honest and consistent. So when our colleagues read that our result is m hat plus or minus sigma, in their mind, they assume that this interval, m hat minus sigma to m hat plus sigma, has 68.3% probability to include the true value of the parameter being estimated. So we better ensure that this is the case, because if it's not the case, we are misleading our colleagues, we are misleading the community. We are selling a result that seems to have a better precision than it actually has. And so this is why coverage is generally desired and expected in high energy physics, even from Bayesian measurements, actually. So also our friends and colleagues that are Bayesian, they would be uncomfortable if upon measuring something, they found out that the results they get have very wrong coverage. And you have to understand that coverage is not a property of the single measurement, but it's a feature of the procedure that has obtained such measurement. So it's a bit like in linear algebra, when you define a vector as an element of a vector space, a confidence interval is an element of a set of intervals that have coverage under repeated sampling. So this is to say that coverage is a big deal, and it's very important to ensure that your colleagues' measurements do have coverage, and that coverage is actually studied in the determination of the results. This is some kind of a sketch that is trying to imply that coverage is not something that applies to your own measurement, your own interval, which is one of the many possible you can get under repetition, but it's a statistical property of the set of the intervals. And so far, it's a while I'm advocating for usage of the maximum likelihood estimator, because this is your go-to solution in most of the problems you will encounter. But there are cases where the maximum likelihood estimator fails. And those cases are typical cases where the parameter being estimated, so m, which in this case is theta, I'm sorry for the change of notation, is basically determining the range of the data. So if the range of the data depends on the value of the parameter you're trying to estimate, this is one textbook case where the maximum likelihood estimator will fail, and you shouldn't use it. You should use something else. Of course, there are other estimators. Not everybody use maximum likelihood, and perhaps the most notable is the least square or estimator, which is derivable from the maximum likelihood estimator in Gaussian problems, and is basically if you have n independent observations, x1, x2, xn, and if they fluctuate following a Gaussian distribution of known variance sigma to the square, and they fluctuate around their known expected values, that are function of a known control sample X with Y, then maximizing the Gaussian likelihood corresponds to minimizing the least square estimators of N. Okay? And therefore, you get a very solid estimator, which in addition to the maximum likelihood, it gives you an important element, which is the goodness of fit. So since we know what is the distribution of our estimator, which is known to follow a chi-square distribution, then I can compare the value I obtain with the distribution I know and determine a quantitative estimation of how my fit is good for the data I have. This is, the least square theory. However, you have to notice and remember that these red conditions here above are almost never respected in any real problem. Of course, you have to make sure that fluctuations are Gaussian, and this is already a non-trivial fit, especially if you don't have many events. But also, you have to ensure that the variance of your fluctuation, this sigma that is a denominator here, is known. And known means is exactly known, means that there is no uncertainty to that, which is, of course, a case that never happens. So what is usually done is that we approximate this ideal known variance with an estimate of the variance that we get from our data themselves, and hope that the least square properties still hold even with this approximation, which is often the case, in fact. And this is just to reiterate that, to my knowledge, it doesn't exist any consensus on the existence of the goodness of fit for a maximum likelihood estimate, especially in the unbinned case. There are some books, including Cowan, which suggest to use the distribution of the maximum likelihood to derive goodness of fit. But there is this nice paper from Joel Heinrich, which showed that this is flawed, this is wrong. And then there are some colleagues who have discussed here and there heuristic methods that may work in simple examples, toy experiments. But my knowledge, there is no yet any mathematical demonstration that this actually works in general, which is what you would be interested in having. So maybe this is a good point to stop, unless I have additional time, which I can use to go ahead. I don't know what Jim prefers.
Hi, Diego. So I think it's probably a good place to pause, actually. We have one more lecture this morning. So Aoife is here. So
Okay.
maybe we should take any questions now on the likelihood and estimation. I actually had one.
Oh, I'm scared.
No, just wondered, you didn't mention, say, about scanning the likelihood and getting the intervals from the how the likelihood is changing, this up certain values to get contours and things like this. So you talked about the toys, which is great, but is there any specific reason you didn't mention this, or because I'm concerned for the tutorial this afternoon, actually. So it's
I was planning to say it, but it was coming from the interval estimation. Let me go to the slide.
Okay.
Where is that? Yeah.
So yeah, this kind of plot here. Yeah. Okay.
Yeah, I have this now. I don't know how actually clear it will appear, but I can try to say this slide quickly right now so that.
No, I think it's okay actually, Diego. I can give them the example and then we can cover it again.
Okay.
Tomorrow, because there's one of the exercises about the lifetime where we'll do these intervals. So that's fine. That's fine.
Okay.
So was there anything else? I don't see anything in the chat. Yes, it's a lot to digest if you've.
Yeah, I'm sorry.
Not to see. No, no need to be sorry. It's great that you can give these lectures and it's very, very clear.
It's difficult to pick everything online if you have never seen these things. I know that, and I really encourage students or everyone else to send me email even today or after those lectures in the next weeks if they're unclear on things, because I know that no matter how one tries to be clear and simplify, concepts are a little bit subtle sometimes. So
yeah. Anyway, we'll have.
Hi. Diego,
hello.
This is Shirin. I have a question, a general one. So in case of B physics, where the data is constantly updating and changing, as you mentioned in your lecture that there are two ways, Bayesian and frequentist. So I was wondering that is it computationally more difficult to use Bayesian because one needs to assume priors when, for example, when the data is changing? So do you have comments about you?
No, I think that
approach.
Unfortunately, no, I think that well, the fact that data is changing is actually a good thing. I mean, you get more data since they are independent from each other. This adds to the precision of your final things. And the computational difficulty, in my experience, is if you want to do things right, because if you want to be sloppy, it's always, it's always possible. But if you want to do things right, the computational difficulty is equivalent in both approaches, because in frequentist approach, you spend a lot of computing power in simulating and fitting toys, so simulated experiments, and this takes a lot of time. And in Bayesian multidimensional problem, you spend a lot of time in doing numerical integrals that are needed for marginalizing, so integrating out the non-relevant variables. So I would not see any particular advantage in either direction in this case. I don't know if this answers your question or not.
Okay, yeah, thanks.
Okay. If there's nothing else now, thank you very much, Diego.